I had to get a thumbnail for the video, so that's going to be today's thumbnail. And yeah, we're back for daily LeetCode day 150 question mark. Nonetheless, we are here back again to be bullied by the LeetCode developers. You know, it's getting personal at this rate, so hopefully we'll be able to stop them soon. Someone has to restore balance to the four nations: DP, graphs, math, and yeah, the final nation. It's unknown, but someone has to return the state. Someone has to return balance to the four nations. So it's either going to be someone from the hyperbolic coding chamber or no one. So fortunately, the hyperbolic coding chamber is in deep recruitment. So if you haven't joined the Discord, you should, because we're getting ready to fight. Okay, this is getting weird, but we're going to stop there. I have some comments today. We have Sean Turner, pretty new to coding. This is in C, right? Oh, yeah, we have someone, Frozen Fire. This is in TypeScript. True indeed. True indeed, brothers. So, yeah. We have another comment from Halston Silenton. That's kind of a cool name. Found your vids earlier today. I thought you were dumb for not seeing something obvious in one problem. Then on the next problem, I didn't see something that was obvious to you. Keep up the grind. Mike. True. That is truly how it be. Appreciate you, brother. True. That's really how it be. That is truly how it be. Yeah, most of the time, I feel like a lot of the solutions I try and do are pretty strange, because I refuse to not work the way my brain wants to, even though oftentimes there are better ways. So for example, the DP problems. I should just write a native maybe there's no such thing as a native DP solution, but there's a trick to the problem. You linearize the sub problems, and then you DP it. But yeah, I just can't help but I have to use a graph, and so this creates more issues than it's worth. And then we have great words from Island Eagle. As always, I slit the sheet I slit, and on the slitted sheet I sit. Yeah, I'm getting pretty good at these. So yeah, we didn't do the morning session today, which was unfortunate. I realized the cheat code of the secret serum to wake up early, and it was to go to bed early. And we did that yesterday, but I think it just be like that sometimes. I just couldn't get to bed. Usually I read before bed, and I was reading, and I just couldn't get to bed. So I don't really know what to say about that, except that it just be like that sometimes. And yeah, so I woke up, and I just woke up closer to work time, and just ended up working instead. That being said, we have to do a shorter session today, to most procure sustenance from my stomach. And that being said, we're going to aim for 40 minutes today, and hopefully we shall be rewarded with great treasures upon frying today's problems. I also switched back from Arc to Google Chrome, so I have no problem. I have no idea what problem we were doing yesterday, or if we were stuck on a problem. Oh no, we were. It was a graph problem, or a problem I was trying to make a graph. It was something like that. We'll find it though. We'll find it. And yeah, we are back. I had to do a quick warm-up. I always forget sometimes, so we did the warm-up. And now it is time to do some LeetCode problems. I didn't factor in the warm-up time, so I'm going to bring the time down to 30 minutes. But first, I want to make sure I can find the problem. So let me see if I can locate that. All right, I found it. It took way too long. But we were working on a problem called diameter of a binary tree. Pretty much you're given a binary tree, and you want to find pretty much the longest path between any two nodes. That's going to be the diameter of the binary tree. The answer to this one is 3, because you can go from 4 to 2, 2 to 1, 1 to 3. Thing to note is that you can pass through the root, so the answer we're supposed to return here is 3. I think we originally tried a solution that always assumed the longest path through the deepest depth from the left subtree and the deepest depth from the right subtree, add them together. This worked for a lot of cases, except I think the last 10 or so, where it turned out that the deepest depth was actually not that. It was between two other nodes which had a longer depth. So what I decided to do instead is to view the tree as a graph. And the way we can do that is just by having access to the parent node. So with each node, we get access to the left and right child nodes. With each tree, we get access to the left, and with each node, we get access to the left and right child nodes. So the way to fix that is so that we can treat it like a tree is that we can go downwards, but we need to be able to go upwards. So we created a parent array, which based on the order we traversed through the tree, allowed us to look up a node's parent by its ID, and the ID is by the order of the tree, the order it was traversed through with the DFS. So to create the parent array, we actually do is call a function called collect parents, which if a node exists, it pushes the node's parent onto the array. We do nodes.push node, and also keep an array of all the nodes, and then we give that node an ID. Then we do the same thing for the children, passing in the parent. Now I realize why I stopped using Chrome, because we get visual artifacts. Passing that node's parent into the collect parents function. Then we iterate through all the nodes in the tree and do a DFS. The reason we're doing a DFS is because when we view the tree like this, when we view the tree as a graph, right, the one with the farthest path from the node is pretty much the deepest level of the DFS tree. So if we look at 2, right, if we look at 2 and we visit it like this, 2, right, the next level below the 2 would be 4, 5, and 1, right, which means you have a length of 1 right now, and then the next length after that would be 3. The next node after that would be 3, which means we have a max length of 2 when we start from 2. If we start from 4, the first level is defined by our children plus our parent, so we pretty much only have access to 2. That's our first level. Our second level is going to be 5 and 1, and if we take a look here, we know that we have to use a visited set or something to pretty much mark our ancestors so that we don't revisit them. So we don't revisit 4. 5 and 1 is our next level, and the only node, right, if we look at the children of 5 and the children of 1, and the parent of both, is the only thing that we can do is add 3, and we get a length or a max level of 3. Unfortunately, when we run our code, I think we might be getting lost in some implementation sauce because we work for the first few cases. We're failing for another case, which I don't think is that far. I think it's like the third case or something like that. Also, DFS is low-key trash in JavaScript because we don't have a native implementation of a deque, which means anytime we pull anything off of the queue, it's actually really slow. So we see here that our root is 312. Oh no. Just realized that our ID is 15, which doesn't make any sense. Our ID should be 3. Maybe it shouldn't. If we're given a simple tree, well, let's see. We'll test if we click run and it works now, then we have a runtime issue, I guess. Oh no, it doesn't work. But our IDs are lower now, which doesn't quite make any sense. I'm wondering if I remove all the test cases and just play this last one. Ooh, yeah, okay. So that's what I thought was happening. It looks like this space up here is kept as, or I guess how they're running these tests, how they're running this. All I know is that the variables up here are being persisted, which is interesting because I assume these functions were just being called. But I guess I'm closing over ID, but I just thought they were getting new space every single time. If that's the case, I think we can fix this by just saying ID equals 0 once we call per diameter of a binary tree. Then if I reset the test cases and paste this one back in, we end up with TLE. And also, I should probably remove all these console.logs. It's just that one. The ghetto part is that we're just gonna have crazy time complexity. We should learn a deque so we can implement it on the spot. All right, so I think our solution does work pretty effectively. And I think the time complexity here should be DFS in this. Takes us linear time to create the parent array. And then here with DFS, we end up with something a little ghetto. So we have DFS. I'm pretty sure this should run in linear time as well. Yeah, this should run in linear time. And then we're running this in a loop, so we should get n squared, but I think we're getting n cubed. Which is always unfortunate. You know what? Let's just do it. Let's just see. We'll keep the implementation very simple. We just need constant time insertion and at the front and at the end. And at the end, we get that for free. I'm pretty sure this is just a linked list low key. So we just need a node. Yeah, so what if we just had a node? And if we keep it simple, what are we using on Q? We're just using push and shift. So we can just implement those two methods. Have push, and we'll also have shift, which is just going to take an element from the front. Do this with a linked list, then we could have something like head, which is equal to new, we'll just call it LL node. And then we'll create something up here called LL node. And it's going to have value, which is going to be a number. And it's going to have next. Yeah, it's just going to have next, which is going to be an LL node or null. But for this sake, it'll be equal to null to start. As a constructor, it'll take val, which can be a number, and next, which can be an LL node, or null, which just say this dot val equals val, and this dot next equals next. I don't think we need anything else. We'll just say it's equal to infinity. So head will be equal to LL node. So whenever we push an element onto the end, I think you need to make this a doubly linked list. So I have prev, which will also be the same, and prev, which would be an LL node or null. Make this a little smaller so it's easier to read, which means you're gonna have head and tail. Which actually means we're gonna have some code in the constructor, and I think we have to set head.next equal to this dot head.next against this dot tail, and then this dot tail dot prev should be equal to head, or this dot head. Yeah, and I think with the doubly linked list, you only need access to one node to constant removal and insertion at the end. So we can just say push. And I actually think they call it pop front. And so we'll just change anywhere we had shift to pop front. We'll change anywhere we had Q to deque. Wait a second. I think I'm getting confused. We want a linked list of nodes, basically. So this is a little bit nonsensical. The value that's actually stored is actually just going to be the tree node. So we can just make it a tree node, and we'll say this dot tree node equals tree node. We have, let me see if we can speed run this. And then we're also going to need length. So we'll have length, which is just going to be equal to 0, basically. And then, yeah. And when we push, what we'll actually do is have Tn, which will be a tree node. And we'll do this dot length plus equal 1. We do pop front. This dot length minus equal 1. And pop front should return a tree node. Okay, so now we need to implement this. I'm pretty sure if you're adding a node from the front, you just need to, if you basically would have 2 nodes, right? If head and tail, right? So you'd create the new tree node. We'd have head and tail, and we want to add they're connected to each other. We want to add a new node in the middle. So to do that, we'd say const LL node be equal to a new LL node, where tree node is actually the tree node being passed in, and we'll just leave the other 2 to be null. But when we push, when we push a node on, we'll have a new node. We want to say head dot. If we have a node there, it's going to be pushed back 1. Yeah, I'll pretty much have 3 nodes in play, with the third node being the displaced node. We're going to have the head node, the new node, and the displaced node. Displaced node will be equal to this dot head dot next. And this node's pointers are going to have to be updated but just the previous one. So the displaced node, it's already pointing to the next node, which is fine. Displaced node dot prev should be equal to the new LL node. And then the LL node dot next should equal the displaced node, and the LL node dot prev should equal this dot head, and then this dot head dot next should be equal to LL node. And it's a lot of node updates there, but the 2 pointers of LL node get updated, the previous point of displaced node gets updated, and this dot next gets updated. I just realized I just did push front. And this doesn't really make any sense, because we want to do something like push back. So to do push back is probably even simpler. We'll still have something like a displaced node, except it'll come from this dot tail dot previous. And then displaced node dot next should be equal to LL node. LL node dot next should be equal to this dot tail. LL node dot pre should be equal to the displaced node. And then this dot tail dot prev should be equal to LL node. Now, if we want to pop something from the front, the displaced node is going to be this dot head dot next, and we just want to make sure that we do one thing really quick. Instead of this dot length equals 0, we're just going to throw error, can't pop. So we're going to subtract 1, right? The displaced node is going to be the node that we're removing. So we'll say displace, we'll return the displaced node. And then, right, the displaced node is the node we're removing, which means we're popping from the front. This dot head dot next should now be equal to displaced node dot next. And that's the first way to do it, because we have to tie that loop around first, and it's going to be removed. And then displaced nodes dot next dot prev should now be equal to this dot head. So we pretty much have a node that's in the middle between head and tail. This dot head dot next, that pointer is now going to move to tail, which is perfect because we're doing displaced node dot next. Displaced node dot next, which would be tail dot previous, should now be equal to this dot head. Then we can return. So let's see if this works. So this does not work. Oh, we want to do two things. We want to do deque dot pushback node dash dot deque dot pushback null, because we have to start it with something. Much faster. The first 3 test cases were. The time complexity is crazy. The time complexity is actually crazy. I wonder why that is. This actually takes 5 seconds. That is crazy. Maybe you don't need, maybe you could probably do less work here, because I'd iterate between all the nodes in the tree. Presumably the shortest path must start at an edge and end. Must start at a leaf and end at a leaf. So probably don't need to do that. So instead of creating something like all nodes, what if we just did something like if node dot left and node dot right doesn't exist, then we'll do nodes dot push Oh, this is much faster than before. Because last time it took 5 seconds. This time it takes 1.5 seconds. Interesting. I'd be curious to see which parts actually take the longest. Collect in terms of milliseconds. Yeah, we can just do end minus start. And then I kind of want to do the same for the portion in here. This kind of looks like spaghetti. And I'd be curious to see which parts actually take the longest. I guess the trees are so small. What if I just did this? Interesting. Interesting indeed. Yeah, I don't understand why this takes so long. But we will take it. I guess the time complexity of this is linear time to visit all the nodes in the graph. So you need to build the parent array to view it as a graph. Maybe there's a better way to tell the diameter of the tree. So I think that is where we will stop.